As we look at this integral, if we wanted to do trig sub on it, I want something squared plus something squared, or something squared minus something squared, and I don't have that. So what I'm going to do is actually complete the square on the first two terms so that I can get that. So I'm going to have x squared plus 2x, half of the middle is 1, squared is still 1. So I'm just going to steal the 1 from the 26, and so that'll leave plus 25. Now this will factor into a perfect square, so I'm going to rewrite this integral as dx over x plus 1 squared plus 25. Now I can do trig sub on that. I'm going to draw a triangle. And I see that I have something squared plus something squared, so I know those are going to be the two legs. I'm going to put the x plus 1 here, and this one 5. If we did a Pythagorean theorem, this side would end up being x plus 1 squared plus 25. And so here's my theta. I know that tangent theta is going to be opposite over adjacent, and then I'm going to multiply the 5 over there. If I find dx, that's going to be 5 secant squared theta d theta. So now I'm ready to do the substitution. I'm going to replace the dx with 5 secant squared theta d theta, and that's divided by, oh, I left the square root off this. That needs to be on there. And I've got x plus 1, which is 5 tan theta, but it needs to be squared, so that's underneath the square root. I'm going to have 25 tangent squared theta, and then plus 25. So seeing what I can do to simplify this, in the denominator I'm going to factor a 25 out, which will leave me a tangent squared theta plus 1, which I know is secant squared theta, so that's going to be 25 secant squared theta. Then I can take the square root of both pieces and leave me 5 secant theta in the denominator. We're going to cross all these out because my new denominator is clear down there. And then one last step, the 5's will cancel and one of these secants will cancel with the denominator. So all of that gets me to the integral of secant theta d theta. Now, if you can remember this, have it memorized. It's kind of a weird one, so it's not one you necessarily would, or you could look it up on an integral table, or I'm going to show you how we actually found that integral to begin with, and that was we are going to multiply by secant theta plus tangent theta. And we're going to do it top and bottom, so to keep this equivalent. Let's see, I still need the integral. Secant theta plus tangent theta d theta. And what that does for me is it lets me do a u substitution. And if I let u be the denominator there, secant theta plus tangent theta, then my du is secant theta tangent theta plus secant squared theta, kind of right there by the edge. That's exactly what I have here because this could distribute through, so, and I should put d theta, and it's kind of off the edge, but that's exactly what I have in the numerator. So my integral is just 1 over u du. So I replaced the denominator with the u, and the numerator was the du. So if I integrate 1 over u, I know that's natural log absolute value of u plus a constant. And then putting back in what u was secant theta plus tangent theta. So I've got natural log of secant theta plus tangent theta plus c. And then my final step is going to be to get that back in terms of x. Well, let's see. How can I figure out what secant theta is? I can look at my triangle, and we know secant is the reciprocal of cosine, so instead of adjacent over hypotenuse, it's going to be hypotenuse over adjacent. So it's going to be natural log absolute value hypotenuse. I don't need to write that factored out now. I can write it back like it was in its original form, which was x squared plus 2x plus 26, although it's not wrong if you leave it factored. That was hypotenuse, and adjacent was 5, and then plus, and I'm out of room. I'm going to have to squish it in sideways. Oh, I think I can fit it because it's the tangent, which is opposite, x plus 1 over adjacent, which is 5. And on the end there was a plus C that's kind of off the screen.